Welcome back to the physics module. In our last video, we learned about wave-particle duality, the fact that things act both like particles and waves. But this leaves us with a problem. If an electron, which is a solid piece of matter with measurable mass, is acting like a spread-out wave, where exactly is it? To answer that, we have to take a look at one of the most famous experiments in science, the double slit experiment. Let's set up the experiment. If we have an electron gun on the left, in the middle we have a barrier with two tiny vertical slits cut into it, and on the right we have a blank detector screen that records exactly where the electrons hit. If classical physics is correct and electrons are like tiny balls, if we fire a machine gun of electrons at this wall, then what do we expect to happen? Well, most of them will bounce off the solid barrier, but the ones that make it through the slits should theoretically travel in a straight line and hit the back screen. So over time, we would expect to see two distinct vertical bands of dots on the back screen, directly behind the two slits. But as we learned last time, when scientists actually did this, that isn't what happened at all. When they fired the electrons, they didn't get two bands. Instead, they got what we call an interference pattern. Instead of traveling like particles, the electrons traveled like waves. The big wave hit the two slits, split into two new waves, and then those waves crashed into each other. Where the crests or the top of the waves met, they added together, creating those bright bands where lots of electrons hit. When the crests and troughs met, they canceled each other out, creating blank spaces where none of the electrons hit. This proved that matter acts like a wave, but it didn't solve our mystery. The scientists realized that maybe the electrons were just bumping into each other midair, causing this wave-like splashing effect. So instead, they decided to launch these electrons one at a time, so that there was no chance of the electrons bumping into each other. After doing this for a really long time, with thousands of single dots eventually piled up on the screen, again, there was an interference pattern. But this is kind of confusing, since only a single electron doesn't seem to be able to create an interference pattern by itself. After all, in order to interfere with something, there has to be at least two overlapping waves. This means that the single electron must have traveled as a wave, passed through both slits at the exact same time, and interfered with itself before hitting the screen as a particle. Until it hits that back screen, the electron does not exist in a single location. Instead, it exists in what we call a superposition of all possible paths. It goes through the left slit and the right slit and neither, all simultaneously. The scientists were really rightfully confused with this, so they set up a detector right next to the slits to watch the electron and record exactly which slit it went through. Again, they fired a single electron, and the detector reported that the electron went through the left slit. Everything seemed as expected. But when they looked at the back screen, the interference pattern was completely gone. The moment the camera turned on, the electrons stopped acting like waves. They went straight through the slits and formed two boring classical bands. By simply looking at the electron, the scientists reduced the position of the particle to just one of the two slits. In other words, the superposition was destroyed, and the wave collapsed into a single particle. This is what we call the observer effect, and what it says is pretty simple, but one of the biggest limiting factors in quantum computing. Put simply, it's impossible to measure a quantum system without permanently destroying its superposition. This is the ultimate trick to quantum computing. A classical bit is a particle. It's locked as a 0 or 1. But a quantum bit, or a qubit, which we'll be talking about more in depth, operates in a superposition. It can be a 0 and a 1 at the exact same time, allowing you to explore massive search spaces, like our book of names from the computing module, a lot more quickly. But because of the observer effect, if a qubit gets bumped by even a stray particle of heat or a tiny bit of radiation, the universe technically observes it. The wave then collapses, the superposition dies, and the calculation is instantly destroyed. Don't worry if this is a little hard to understand right now. In the future, we'll be building on these ideas a lot, and you'll be hopefully getting some more practice.